Whoops. Okay, please project. Okay. Go. Okay. In Casey's journey through why is technology failing her, my Surface Pro 7, which is on Windows 11 and keeps crashing, so this is on recording, y'all, is refusing to listen to my DisplayPort right now. So you can see the course slides on the class webpage. There's a warm-up to get started with hashing, and let me restart this machine and see if I can convince it to project for a second, all right? Microsoft. The death of me. Okay, please. We're just going to restart. And in the meantime, can I log into this desktop? Okay, fine. Oh my God. Yeah? Oh, are the slides not on the course website yet? Okay, hang on. Are you fucking shitting me, you piece of shit? Okay, hang on. Are you shitting me? Why? Why would you do this? I literally just think this Surface has decided to die. This Surface is less than a year old. Oh, that's very nice of you. Right now I am attempting to sign on to the desktop to computer. Oh, really? Okay. Oh, wait. I just got in, and unfortunately, I won't be able to use annotations. Let me see if I can even just get this chair to go down. Somebody, please. Okay, let's see. Okay. Okay. All right. Okay. I swear, is it like the Surface knew that I directly abandoned my Microsoft roots to go work at their direct competitor for teacher devices? Is it punishing me, or is it just validating my choices? Wow. God, Surface Pro, I've been teaching with you for years. I don't know what your problem is. And then I bought a fancy new one. Okay, I'm sorry. I'm just salty as AF right now. Okay. Sweet. Look, there's a warm-up. It's on the screen. It happened. Thank you all for your patience. And forever, we will remember that just because maybe you get a computer science degree doesn't mean you know anything about the actual functioning of technology, i.e., I'm terrible with printers. I'm sorry, Mom. I will never be able to fix your printer. Okay, cool. So, sorry, in the interest of time, let's talk through this together real quick. So we're picking back up where we left off on Wednesday with the magical world of hashing. Now remember, hashing is really just a way to translate a piece of information, like a key in a map, to a specific, what we're going to call bucket in a hash table. This hash table has 10 buckets. And we would like to insert these key value pairs into this current hash table. Our first bucket is, or our first entry has the key of 2 and the value of B. Using this little function here, what index is this item going to show up as in our hash table? I heard somebody say it. Yeah, I agree. Okay, great. Okay, our second item has a key of 3 and a value of C. Which bucket is it going to show up in? 3, I agree. Okay, what about 10? 0. Yeah, okay, we got it. What about 9? There's a method to the madness. What about 1? 1. What do we think is going to happen now? Great. I guess it's supposed to belong here, but that space is already occupied, right? Congratulations. This is what we call a collision. So remember what we were talking about on Wednesday was the idea of like, okay, well, what if we had that direct access map where we made enough spaces for every individual possible key, but that would be like a lot of wasted space. So we went to this hash table where we've got this translation from item to bucket. But because we're doing this translation, it means that multiple things could hash to the same location, thus causing a collision. So remember when we looked at that like ideal runtime of the direct access map, it was like constant time ones, everything's like instantaneous lookup, instantaneous. Now we have to figure out how to keep ourselves as close to that runtime, but solve this problem, because moving to the hash table solved the problem of a bunch of wasted space. But for the rest of lecture, I'm going to talk about what we deal with in this situation where we have a collision. Does anybody have any, how do I go back? Wait, I got it. Does anybody have any questions on this before we dive in for the rest of the day? Cool. I know the poll everywhere has nothing to do with this. It's a fun word cloud. Also keep in mind, I do not look at your answers to this. So feel free to fill out that poll everywhere and get your extra credit point. And then at the end of lecture, let's look at the word cloud we make. See what happens. Okay, announcements, reminder, exercise 1 is due tonight. Exercise 2, I believe, has already even been posted. Thank you, amazing TAs. And exercise 2, like I mentioned on Wednesday, is going to have some recurrences in it for you, and it's also going to have some design decisions for you. We are going to start to get you practicing for the simulated midterm that will be coming out in week 6, because it's week 3 right now, right? Yeah, 4, 5, yeah. I think week 5 or 6, I can't remember. April 29th, whatever week that is. And that midterm is going to be entirely design. So I'm going to give you a scenario. I'm going to ask you to pick how you would design the code for that scenario. So it's a good way to practice on this exercise 2. We're going to have another practice round for the midterm in exercise 3. Also, reminder that project 2 is officially out. It is a 2-week deadline and a 2 weeks worth amount of work. So please start early. Does anybody have any administrative questions? No. Okay. Okay. Man, it really sucks to not have my pen. Okay, so here's our sort of like roadmap to what we're learning here. So we talked about that sort of direct access map, and then we talked about that simple hash map, but then we hit that problem with the collisions. So what we're going to be learning about today is something called a separate chaining hash map, which is specifically something you will be implementing in your programming assignment. So, there we go. I know Project 2 actually has 2 different pieces of it, so you can get started on the first piece, but after today, you'll be able to finish the entire thing. I believe we just got to this part where at the end of lecture where we were defining this idea of a hash function. And really, just by definition, a hash is just a translation of a value into a place it can live in the hash map. So your student number is 6 digits long. We do some magical translation on it, and we find out it can belong in bucket 3. That's what the hash function's doing. And so technically, I've been kind of giving you this like really, really crappy hash function where actually the hash function is just like mod by the table size, right? And actually, it turns out I'm actually really just using the direct value as the key, and then I'm just fitting it into the bucket. We're now going to do a lot more fancy translation and what we do in those situations. So we talked about mod. Yep, we use that. I believe this was our example where we saw the collision, or was this the example? No, this one's the one where we don't have a collision. Looks good. Nice. So here is what the hash function looks like. Cool. Then this one was the one where we saw our collision for the first time. Oh no, what happens? Great. So I think I mentioned this briefly in lecture on Wednesday. This is sort of like the big problem to solve when it comes to hashing. So when you're building a hash table, there's kind of 2 big fundamental designs that you need to decide on. And the reality is there's no perfect answer. You're always going to be trading off some amount of runtime for some amount of memory, some amount of hash computation for some amount of collision resolution. And so this is also something that I might ask you to think about how you would design a hash as part of the midterm. So, future idea, the goal of this is we know that when we had that direct access map, everything had its own individual reserved spot, right? There was never going to be a collision because we were guaranteed that there was more than enough spaces for every individual. And that caused us that perfect instant lookup, instant runtime. So the closer we get to that state, the closer we get to that runtime. Meaning the more collisions we have, inevitably, the slower our runtime will be. And I'll show you where that comes up. But we show you that direct access map so that you can hold in your mind, like, what's that North Star? What's that state I'm ideally trying to shoot for? And then as we're designing, we're always keeping in mind, what choices are we making that's taking us further away from that? And is that a fair trade-off? So by reducing the size of the underlying array, I gained the value of not wasting all of that space, but I lost a little bit of the runtime because now I might have some collisions. So that kind of trade-off is specifically what I'm asking you to pay extra close attention to. So We have two questions that we have to answer for ourselves, and these are the two big areas of design when thinking about hashing. One, when we have a collision, how do we resolve it? What do we do with that collision instead? Two, how do we minimize the number of collisions? So we know that like a collision is probably going to happen. Like that's just the reality of having fewer buckets than possible values of entry. But we also want to do our best to minimize as many times as that happens. So there's a bunch of different strategies to handle collisions. And the first one, and the one we're going to spend pretty much all of today talking about, is something called separate chaining. There is also a whole category of things called open addressing, and we will talk about those as well, just so you have kind of a purview as to where we're headed here. Here is separate chaining. I like to think of separate chaining as the least computationally complex approach to handling collisions. And what separate chaining literally means is, oh, if we have multiple things that are trying to hash to the same spot, let's just let them both live there. So the way that you do that is that instead of making an array of pairs like we have, where every entry immediately went into the bucket of the hash table, instead, we're going to make an array of linked lists. And what that means is when you have a collision, like you can see here in bucket 1, if I have a collision, then I just add another node onto a linked list. So as you can see, we've got some buckets that are empty. That means those buckets have a null pointer for their linked list, like index 0, index 8. So those are null linked lists in that case. In boxes 2, 3, and 4, we've got items that have hashed there. We've got that one thing. So we've got a linked list with one node in it. And then you can see we have our one collision in bucket 1, where originally the value 1 hashed there, and then later somebody tried to insert the value 21. It hashed to the bucket 1, and instead of, jettisoning it away, we're like, come on in. There's room for everybody in each bucket. Any questions about the basis of this idea? This is the foundation of separate chaining. It's literally just the idea that when we have a collision, we just have a collection at each bucket so that it can hold, each bucket can hold multiple entries. So here's how some code might look. And in my opinion, the code that you will probably ask the most questions about when you are doing this yourselves is, how do we then find what we're looking for in these hash tables? Because before, we could just immediately reference the index of an array and just assume the thing that's there is the thing we're looking for, right? In separate chaining, one of the sort of trade-offs we make for the simplicity of just storing multiple things in a bucket. So this is like simpler to implement than the other ones I'm going to show you. What we lose in exchange is it means that when we compute our hash function and we find our bucket, it means we might have to do a little more work to continue and find the thing we're looking for. So you can see right away is here's us sort of computing that hash. So we take in a key that we're looking for, we modify data length, and that tells us which bucket it's supposed to live in. And then what we have to do is we have to accept that there might be multiple things. So we have to then go loop through whatever linked list is actually stored at data at bucket index. Return true if we find that key. Return false if we didn't find it in that linked list. So if I'm looking for the value 21, I would say 21 mod table size. That would give me the value 1 because the table size is 10. So 21 mod 10 gives me 1. I would then come in and I would say, this here is a front pointer to a linked list. I am now going to loop over that linked list. And I'm going to come in and I'm going to say, okay, front.next, are you 21? Nope. Front.next.next, are you 21? Yes, I found it. let's say, for example, I was looking for the value 31. I would do the same thing. Front.next, are you 31? Nah. Front.next, are you 31? Nah. Oh, and that's the end of my linked list, and that's how I know 31 is not in my hash table. So, if you can tell where we're headed with this, can anybody guess for me then, what is the absolute worst possible scenario for a separate chained hash table? Yeah. If everything lives in one of the buckets. And right now, there is nothing that is preventing that from happening. It's entirely dependent on the state of my data. But I could end up having let's say I have a data set of 10 items I'm trying to store in a hash table. And what if those 10 items are 1, 21, 31, 41, 51, 61, 71, 81, 101? Then I don't actually have a hash table anymore. I've got this sort of degenerate hash table that secretly just turned into a linked list. And in that scenario, if I was looking for the value 101, what would the runtime be in order to find that thing in that terrible degenerate hash table situation? Yes, I love it. Yes, I absolutely agree. All of the items ended up in this singularly linked list in this singular bucket. So the runtime to find that thing in the bucket, then in a worst case scenario, could be linear, because I might have to look at every single thing because I'm just looping within a bucket. That's our worst case scenario. What can anybody tell me would be our best case scenario? If the worst case is every single thing hashes to the same index, what would the state of the hash table be in the best possible optimal situation? Yeah.
Just got a question.
Sure.
Node adds to the front of that bucket or the end of the bucket?
Good question. So for example, in this context, the question is did 1 come first or did 21 come first? Did we add to the end of the list or do we add to the front of the list? You'll find that generally you probably want to add to the front of the list. So when you're ready to insert things, that's a little bit faster. You don't have to incur any time to just find to the back of it. So generally we add to the front, but if we're searching for things, who knows where it is. So we might have to loop over the whole thing. Did that answer your question? Yeah, cool.
So the best one could be the first one.
Oh, okay. I like that. Yeah, the best case scenario is it's maybe it's the very first thing in that linked list. And so that would be sort of within the best case where everything is all in a singularly linked list, wouldn't it be great if the very first thing that I was looking for happened to be the first node in that list? Our overall state of the hash table's best case is very similar to that, because then what we're saying is the best case scenario is one in which we never have to loop over the linked list, right? What would that table of 10 values look like? Say they're just 10 values. They're not the 1, the 21, the 31, or whatever, just any set of values. What's the ideal sort of state so that we have the best case scenario? Yeah, in the back. There's one node in each index of the array. Perfect. Again, our best case scenario looks a lot like that direct access map, right? No collisions. So our worst case scenario is n collisions. Our best case scenario is 0 collisions. And then what would the runtime be if we had 0 collisions then to find something in this situation? Constant. And if we look at our pseudocode here, right, it essentially means if everything is just one bucket, then this loop here is never really going to be a loop. We're always going to find it at, front.value or something like that, right? So we would have constant time lookup. 0 collisions best case, n collisions worst case. Does anyone have any questions about the distinction between the best case and worst case scenario here? I find that I know best and worst case can be a little confusing, and it makes a lot more sense, I think, looking at it in the hashing kind of state. So, yeah.
I don't have a question between
Sure.
best and worst case.
Okay.
It's kind of confusing
Why isn't the best case when everything's empty? So when we're talking about cases, we're talking about how the code will function while n still tends to infinity. Whether we're going to have n collisions or we're going to have 0 collisions, they both will have a moment where the table is empty and then turns from empty to 1. So that's not a differentiator. Like that case comes up, like that situation comes up in both cases. Case analysis is more about like not the value of n or how many things are in it, but regardless of how many things we're going to insert into our collection, what's the overall state of those values and how is that going to impact our runtime? Really good clarifying question, because I think that specific piece, why isn't the best case always just when it's empty or when I do the first thing? That is exactly what pretty much everybody, that's the sticking point. So thank you for asking that question. Yes, cool. So this is our best case for separate chaining. This is what it might look like as we have one node sort of hanging off of each bucket. So again, this is essentially, again, our ideal state. So whenever we're designing, we're trying to get to this. Again, we're trying to avoid collisions. Collisions become expensive. So here's the runtime that we talked about. If you can't tell, these slides are a little more verbose, mostly because I know you're going to be working on this project, so you can come back through and just read them at your leisure. So I'm not going to be reading all these things, but they're kind of operating in this way, so there'll be a good reference guide for you later. But you can see here, now we've got put, get, and remove, and we've got that array with indices of the keys, the best and the worst case. Now, in this situation, I'm going to add a third case. I'm going to add a in practice case, because to be frank, it would be like really bad luck if every single one of our values somehow ended up colliding into the same bucket, right? Like if I knew that my data set was 1, 11, 21, 31, I should probably pick a different hash function than just hash to the same bucket, right? Or I should maybe pick a different situation. That's not a good data set for hashing, right? But again, like I said, that's kind of like really, really unlucky. And in fact, you'll find that once we start to talk about, and I'll mention this a little bit, how we adjust things to reduce collisions, then we get to some sort of in-between state from 0 collisions and n collisions. And we're going to kind of talk about that as the in-practice case, where it's not either of those theoretical extremes. It's more like what's like sort of functionally going to happen. Now, this could be different, obviously, in different scenarios, but I also call this in-practice case up. And just for context, this idea of in-practice case is something I invented for this class. I think I vaguely mentioned if you take like CSE 332, they'll talk about amortized cases where they do a bunch of statistical analysis and actual like math to figure out what that real in-practice case is. I have literally never seen that come up in industry. So I was like, we're going to talk about in-practice case here so that if somebody asks you about this on an interview, you can give them this sort of general analysis. And so you can see at this moment in time, we still think of the in-practice case as closer to a constant time than an n linear time. And that's because we are going to do some stuff in the next few slides to essentially guarantee that we're never really going to hit that like n collision situation. You'll find that on average, when we sort of bring everything together, you probably end up with like at most 2 or 3 nodes off of a singular bucket kind of thing. And that's a pretty average sort of level of collisions. You can read this stuff for the homework, but I'm going to talk about it now here. The thing that's also kind of weird about this separate chaining situation is I can now store more entries in my hash table than there are actual buckets. If I have 10 buckets and 20 entries, I know there's going to be a lot of collisions, right? Because physically, in order to fit more items into the hash table than there are buckets, then I know that each bucket must have an overall amount of things in it, a load factor, if you will, that is more than 1. That's just like the way the math works out, right? If I'm going to stuff 20 things into a drawer that only holds 10, it's going to be stuffed really tight. So we are not actually trying to make a really dense hash table. That's like a whole different structure. We're trying to stay in that space where each entry gets its own individual bucket. So one of the ways to help us prevent collisions is to make sure that there's always extra space for a new entry. So we are going to regularly resize our underlying array and grow it so that we never get too stuffed. It never gets too overloaded. The way that we use the name that we keep for the idea of how full the hash table is, we refer to that as lambda, the like Greek character lambda you can see on this page here. We call that the load factor. And lambda as a calculation is literally n, i.e. how many things are currently in your list, divided by the capacity of the list. So in this picture right here, C, our capacity is 10. There's 10 buckets. N is 1, 2, 3, 4, 5. So our lambda is 5 over 10, 5 items stored in a table that can hold 10 buckets. So our overall load factor is 1/2. It's half full. Any questions on lambda there? So if you look at our runtime now, we're actually going to say our quote in practice case is lambda, because it's sort of like maybe that's the average of like how full any individual bucket is, by making this sort of logical association that like we'll just assume every bucket is sort of like on average about as full as the overall hash table is. And like I said, like if you do things kind of effectively, like this is actually in my experience pretty relatably average kind of setup for your hash table, where you can see there's only really one collision. That means that our longest chain that we would have to loop over is like too long, that kind of thing. Yeah. Yes, question.
Can you say that the manifest between constant and linear?
Like the runtime? Yeah. Yes. So right now, this is still gonna have like, it's kind of weird because n is a factor, right, in lambda, right? Like it's n over c. So you could almost think of the runtime as like 1/2 n in that kind of way. Because it does matter how many things are in it. It's not just purely constant time. But you can definitely, like, if you were, say, in an interview, you could say, like, oh, like, the runtime is mostly constant. And you'll find that in industry and in interviews with, say, the hash table that Java implements, it has a bunch of the optimization features. It's all figured out. And, like, we're going to get there. I'm going to teach you all about the hash functions and the separate chaining and things like that. So it gets to still claim that its runtime in practice is constant time, because it ends up being so far away. Like we had so many guardrails to protect us from that worst case scenario. So you'll find when you ask somebody in industry or in an interview, if they're like, what's the worst case runtime of your hash table? You could be like, okay, well, hash tables are constant time lookup, constant time access. Especially if you're using the one, say, created by Java or Python. Okay. Up until now, I've been saying hash function. I've been like kind of cheating it a little bit because we've limited our problem. Remember, we simplified our problem to like help ourselves figure this out, and saying we're only going to take in integer values as the possible keys. But what about the actual dictionary situation where my lookup value is a word? It's a string, right? Hash tables need to be able to hold any type of data. So you need to be able to process any type of key and go from whatever the heck that key thing is to some magical place in the hash table that it'll get to live. With integers, since the buckets have integer indices, that was like a pretty direct translation. But what the heck do we do when we don't have integer keys? we're going to have to define a different type of hash function. And again, we're kind of coming back to when we're doing this type of design, what are the two things we're trading off between? And what we're going to try and trade off between is we want a hash function that reduces collisions as much as possible. Hopefully you feel pretty comfortable about why collisions are no bueno. And then we're going to create a hash function with low computational costs. Because if I'm doing all of this work to compute something so that they don't collide, but like just figuring out the bucket that it should go in is really expensive, then it's like I've lost any of the extra like distance gained in runtime by spending it computing the bucket. So I'm trying to make this balance between how can I come up with a good place, like what math can I do to find a good place in the bucket for this thing to live without it spending so much runtime and instructions that I actually just consume all of that good runtime I made for myself in just like the act of computing it. Let me show you what that means. So let's say we are trying to convert the non-integer key into a place in the function. So hash code, like it is here, this method name is a pretty standard method name. Technically, all objects in Java come with their own hash code method. And that is so that if you ever try to hash them into something, they will generate a random number that can then be modded by the table size to make sure that that thing fits. So if I have a string, every string has a .get hash code function inside of it that will spit out some integer number that hopefully is pretty unique. And then when you mod that unique number, it finds its place into the hash table. So every object has its own sort of like internal responsibility to figure out how to provide these numbers to hash tables. So one way we could do that is we could sort of like translate individual strings into some type of kind of identifying number by being like, okay, well maybe like we use the length. And that would be a very inexpensive way to generate a number from a string. Just be like, oh, well like it's already got a field that's called length, just like use that number. It's a number already associated with the string. But as you can imagine, then we're probably going to get a lot of collisions. Like all 3-letter words are going to get indexed to the bucket 3, right? Lots of words have the same length. So there's lots of collisions. So that's a very inexpensive computation. It's very inexpensive to go from a string to a number, but we're probably going to hit a lot of collisions. So let's like, maybe we need to do something like a little more complicated. We need to like reduce the likelihood that these strings are going to produce the same number to represent them. So maybe in another way, we're going to like, okay, well, maybe we want to incorporate a little bit more than just like the length of the string to get this number. So what we're going to do is, in this situation, we are going to loop over each individual letter of the string. And if you remember from 143, Unicode and ASCII are these sort of ways that we have a numerical association with each individual character. It's a way that computers can remember how to find characters. So like, for example, because I'm a weirdo, I know that like the lowercase a has an ASCII number of 96, 97. And then lowercase b is 97, lowercase c is 98, and then uppercase a is like, I think like whatever 97 plus 26 is. Yeah, thank you. So there's ways to sort of convert individual characters to a number thanks to that ASCII encoding. So what if we're trying to generate this like kind of like differentiating number to represent a string? What I could do is loop over the string and take each individual character, cast it to an int, so which is like pull out its ASCII value, like, okay, A, turn that into a 97, and turn that into a sum. So like if I'm trying to, previously up here, let's say the words cat and bat, since they were both 3-letter words, they would both end up in bucket 3. With our implementation 2, we would say, no, add the int value of B plus the int value of A plus the int value of T, give me that sum. That's the number I'm going to mod by table size and put in. because that B is different in bat is different from the C in cat, they're going to have a 1 number difference, right, in those sums. So I am now starting to differentiate more. I'm going to have fewer collisions because I'm incorporating more complexity, the more of the uniqueness of the word in generating this number. But look at the code to get that hash function or to get that hash number out. I now have to loop over every single number in every single string just to get the hash code out. So I've incurred a bit more runtime, but I've probably reduced the number of collisions. Any questions on this sort of approach here? Yeah.
So for implementation too, if you implement it that way, would the size be too big for the array?
Yes. So what would happen then is like I said, like if B is like 97 plus A is 96 plus T is whatever, some number, that's going to be a huge number, right? If somebody is super fast at math, shout out that number. But then we would take that big number, which is probably in like the 300 or something, and we would mod that by table size to make that number fit. So what's different here about these hash codes, and like I said, I was a little cheating before with like the hash codes mod by table size, is that all of these hash codes are eventually going to get modded by the table size. And in fact, this becomes incredibly important because like I mentioned with that lambda piece, that size of the table is going to change regularly as we add things in. So we need a hash code that's independent of the length of the table because we know that the internal capacity of that table is going to grow over time. And so every time we resize our hash table, we actually have to go back in and rehash things, meaning go back in, get whatever number represented it, and then figure out its new bucket in that bigger array. So like it might be in a different spot if the original array was of size 5, maybe 300 something mod 5 is a different value from 10, like 300 mod 10, so on and so forth. We can continue our thinking where if we really start to think about, okay, like how do we get like uniqueness? How do we really get away from collisions? Because that thing where I'm including the letters, right? Bat and cat ended up being 1 number off, but like it's just a sum. So we could have like, let's see, bat and tab, which are both 3-letter words with the same 3 letters in them, just in a slightly different order. They're going to produce the exact same hash code in approach number 2, right? So we're probably, again, we're going to get a few more collisions. But what if we were even trickier? We could do this thing where instead we start to incorporate prime numbers into our hash code, because prime numbers are kind of magical in that we know that they have fewer common divisors, right? So if somehow all of our hash codes were prime numbers, we're pretty much guaranteed that there's going to be no collisions, right? Because they'll never sort of mod by table size collide in the same way if they're prime numbers, usually. Depends. Much less likely to. It's very different if, like, let's say the hash code generated was always something like 5, 10, or 25, right? Like, everything that has, like, something that's, has 5 as a common, divisor, they're going to have a lot of collisions. But the thing about this sort of approach 3 now, though we've caused even fewer collisions, we've included this get next prime method. And we actually already know how expensive it is to get next prime. Do you remember that like time we were talking about when O and omega don't match? That if it's an even number, it's like constant time, but to find primes, you end up having to loop up every number to figure out if it's a prime. So this ends up being insanely expensive. And then also because I was being cheeky, I was like, also maybe like instead of just summing them up, we like make them powers of each other to just get these like crazy numbers out. But actually, as it turns out, this has now officially gone too far. The computation required in order to generate this super unique hash number is now not worth it in comparison to the amount of runtime we would incur for the collisions. So actually, number 2 ends up being closer to what people really use because it's sort of like that balance between like, I want to do a little bit of extra work to get some unique numbers, but I don't want to do so much work that like I eliminate all the goodness here. Like a few collisions is better than doing this get prime thing. So here you can see some of our pros and cons. This also makes, like I said, I was being kind of cheeky. I did this like math.pal. So these end up being gigantic numbers and taking up all this space. It was me just trying to show like you could really get a lot of uniqueness, but this is super expensive. Questions about this idea of trade-off, how we kind of like spend our computation to get to this unique number. Like I said, every individual object has its own get hash code function inside of it. So it's not the hash table that is creating the hash numbers, it's the individual objects. So strings in Java have their own get hash code method, and it looks more similar to what number 2 is. So whenever you're making a new object, you have to figure out what hash code function you're going to use to represent your object. And you can imagine as we get to like complex objects, like let's say we had an object that was a student object, maybe your hash code is just return your student number. Maybe that's pretty good. But maybe student numbers are like, you know, that would be a better hash code than say like the length of your last name. The length of your last name would probably be a pretty crappy hash code because we probably have a lot of names with the same length, right? Maybe the student number is unique and it's already a number, so that's a good one. But what if we didn't have student numbers? Maybe then you'd have to go through and determine some combination of like, well, if I like add your birthday to the length of your name, that's like pretty deterministically representative of you, but it gives me a number that's unique. So it's up to you as the designer of the object to come up with the hash code. Like I said, you can read this for your assignment. Every Java object has this hash code function built into it. And technically, it's like the one method that's in the literal capital O object class. So you can override the function in order to define it. Perfect. A recap of how we kind of get this nice distribution in the separate chaining situation. So first of all, we're going to want to resize our internal array so that we never end up with an overloaded array. Remember, we're always trying to get to our best case scenario of one item in one bucket. So we better resize so that we are not in that terrible overloaded situation where we're guaranteed to have more items than one in the bucket. So we never want our load factor to go over 1. 2, when you resize, here's another delightful trickiness. Choose a table length that will help reduce collisions. If you multiply the array length by 2, then you're always going to have a even number that you're modding by, and that's probably going to cause a lot more collisions. So the actual best practice is you do double the size of the array because we want to, like make it bigger, but then we want to add the nearest prime number. Like we want to use the nearest prime number to that. So if we start with a array size of 5 and I want to go resize it, I would say 5 times 2 gives me 10, but I know that like modding by 10 is probably going to cause a lot of collisions. So actually 11 is the nearest prime number to that. So I'm going to make a table size of 11. And then the next time I come around, I'll make, 21. And then I'll go in and I'll be like, ooh, like maybe we'll do like 21 or like 20. Is 23 a prime number? It is, right? Yeah, maybe we'll make a table size of 23. And you can imagine modding by 23 is going to cause fewer and fewer collisions. And then the final piece, like we just finished talking about, is this idea of designing a hash code so that you have somewhat complex hash codes that are less likely to cause collisions. So 1, resize before you overload your array. 2, pick a new table size that is a prime number. 3, design a hash code that produces a nice distribution of different hash codes. Great. I know I'm out of time, but I'm happy to stick around and answer a couple questions. Yeah. So the prime number thing is because if I'm taking a number and I'm going from that crazy number from the hash code to figure out which bucket it belongs in, I have to do that mod by table size. And modding by a prime number is going to produce more varied results than, say, if like I modded by 5, I modded by 10. Probably a lot of things will kind of collide in that scenario. So adding in that prime number into that calculation is going to cause fewer collisions. Yeah, for sure. Yeah, cool. Okay, wait, how do I do this now? Desktop? I know, I'm like, so weird. Okay, wait. Yes, hello.